This lecture is about subspaces of vector spaces. The idea of a subspace is that a subspace of a vector space V is a subset of V, which is also a vector space in its own right, using the same addition and scalar multiplication that V has. But we're going to see a more helpful definition on the next slide. But before we do, I want to introduce just a little bit of terminology about vector spaces. So if V is a vector space over the field F, so an F vector space, then we call elements of the field F scalars. And that's because those are the things which you can scalar multiply by. So here's our definition of a subspace. A subspace of a vector space V is a subset U of V, which has the following three properties. Number one, it has to contain the zero vector. Number two, it's closed under addition. And what that means is that if you have any two elements of U, then their sum must also be in U. And finally, property 3 is that U must be closed under scalar multiplication. And what that means is that if you have a scalar L, and remember what that means is just an element of the field over which V is a vector space, and you have any element U in U, then the scalar multiple L times U must also be in U. So there's a piece of notation which we use to express that U is a subspace of V, and here it is. We write, U is less than or equal to V like this to mean that U is a subspace of V. Let's take a look at a couple of example subspaces. Firstly, some trivial examples. So if you have any vector space V, then it's a subspace of itself. So V is a subspace of V, and the zero vector space contained in V, so that's just the set containing the zero vector, that is also a subspace of V. So there are two fairly uninteresting subspaces. Let's now look at a slightly more interesting example. So let's take V to be the real vector space R squared, the space of all height 2 column vectors with real number entries. And let's let U be the set of all things or vectors whose first entry is 0. So that's certainly a subset of V, and I claim that it's also a subspace. So if we want to check that it's a subspace, what we must do is to check that those three properties in the definition of subspace hold. So let's do them one by one. So one, if taking x equals 0, we certainly get that the zero vector 0, 0 is in U. So property 1 is fine. Property 2, I have to show that if I have two elements of U, then their sum is also in U. So let's take two arbitrary elements of U. That looks like x, 0x, and 0y for some real numbers x and y. Well, then if you add them, what you get is the vector 0x plus y, and that's a height 2 column vector with real number entries whose first entry is 0, so it lives in U. And that means the sum of two arbitrary elements of U is again in U, so it satisfies property 2. And if we move on to property 3, closure under scalar multiplication, again, if we let 0x be any element of U, and if we let L be any real number, then the scalar multiple L times 0x. And what that is in the first place I get L times 0, which is 0, and in the second place I get L times x. So again, what I've got is a vector with a 0 in the first place and some real number in the second place, so that is an element of U. Okay, U has all three properties required to be a subspace, so it is a subspace of our vector space R squared. Let's do some more example subspaces. And in fact, I'm going to begin with an example of something which is not a subspace. So let's look at, first of all, V is going to be the vector space R squared again, and U is going to be all of the height 2 column vectors with integer entries. So for sure that is a subset of V. And we can ask, is it a subspace? What do you think? Pause the video and try and check the definition for yourself. Okay, the answer is no. U is not a subspace of V. It passes 2 of the tests and it fails 1 of the others. So U passes condition 1 to be a subspace. It does contain the 0 vector because 0 is an integer, so the vector 0, 0 is in U. It's also closed under addition. If you add 2 column vectors with integer entries, then you get another column vector with integer entries, so it's closed under addition. But it is not closed under scalar multiplication. So the reason that U is not a subspace is that it is not closed under scalar multiplication. For example, the vector 1, 1 is in U. There is a scalar root 2 in R, but root 2 times 1, 1 is equal to root 2, which is not an element of U. So we have multiplied an element of U by a scalar, and we got something which was not an element of U. That means U is not closed under scalar multiplication, so it cannot be a subspace. Let's look at another example of something which is a subspace of a vector space. So this time we're going to take a completely different vector space. So we're going to let F be the vector space consisting of all functions from the real numbers to the real numbers. You'll remember that we saw this example a couple of lectures ago. All functions from the real numbers to the real numbers. We're going to let curly U be the subset of F consisting of all functions which are 0 at 1. So little f in curly f with the property that f of 1 equals 0. Then, well, what do you think? Is curly U a subspace of f or not? Pause the video, work it out for yourself. Well, I hope you did that. the answer is, of course, that U, curly U is a subspace of F. And again, if we want to prove this, we should check that the conditions all hold, all three conditions hold. So condition 1, does U contain the 0 vector? Well, you will remember that the 0 vector in our vector space F was the constant function which took the value 0 everywhere. So 0f is the constant function taking the value 0 everywhere. And so in particular, the 0, the constant function which takes the value 0 everywhere, it's certainly 0 when you give it the input 1, and so it's in U. Condition 2 is closure under addition. So let's take two elements of U and see if their sum is in U. So we're asking the question, is F plus G, again, in U? And the answer is yes. Well, we can just check the defining property for being in U. So if we look at F plus G at the number 1, well, the definition of addition in our vector space F is that F plus G at a particular input is just the sum of F of that input and G of that input. But since F and G were elements of U, F of 1 and G of 1 are both equal to 0. So F plus G satisfies the defining condition of U. Finally, condition 3 is closure under scalar multiplication. Remember, F is a real vector space, so we're going to choose a real number L, and we're going to choose an element F of U, and we have to check whether L times F is in U again. So you will remember the definition of scalar multiplication in our vector space. L times F at a particular input is defined to be just L times that input. So L times F at 1 is L times F of 1. That's the definition of scalar multiplication in this vector space. But of course, F of 1 is 0 because F was an element of U. So this is L times 0, which is 0 again. Okay, we've shown that if you take any element of U and multiply it by any scalar, you get another element of U. That means U is closed under scalar multiplication, so it obeyed all three conditions to be a subspace of U, a subspace of F. Okay, finally, one example, which I'm going to leave to you to check. I'm going to think about the vector space of all 2 by 2 matrices. Just for fun, let's take the complex matrices, not that it makes any difference. So let's consider the vector space of all 2 by 2 complex matrices. Let's let U be the subset of this vector space of 2 by 2 complex matrices consisting of all matrices A such that A squared is the 0 matrix. Well, I'll tell you for free that U is not a subspace of M 2 by 2 of C. But I'm going to leave it to you to figure out why that is. So it does obey the first part of the definition of subspace. It does contain the 0 vector, which in our case is the 2 by 2 0 matrix, but one of the other conditions is not true. So you should have a think about why that's not true, and I will tell you the answer at the start of the next video.